Hello, and welcome to today's Safety and Health webcast, Combustible Dust, Flash Fire Hazards, and Protecting Your Workers, sponsored by Westex by Milliken. My name is Kyle Morrison. I'm the Senior Associate Editor with Safety and Health magazine, and I'll be moderating today's session. Thank you all for joining us. We'll start the presentation in a few minutes, but first I'd like to go over some housekeeping items. The views of the speaker and his organization are his own and do not necessarily reflect those of the National Safety Council or Safety and Health magazine. Mention of any commercial enterprise, product, or publication does not mean the council or the magazine endorse them. At the end of today's webcast, we'll have a question and answer session. To ask a question, simply type it in the text box located in the lower left-hand corner of your screen, then click the Submit Question button. You can feel free to ask your question at any point during the presentation. You don't have to wait for the Q&A session to begin. We'll try to answer as many questions as possible, but due to the large number of participants today, not all of the questions may be answered. However, all unanswered questions will be forwarded on to today's speaker. For basic troubleshooting information, please click the Help button located on your screen. At the end of the webcast, you'll be asked to complete an evaluation survey, and I'll talk a little bit more about that after the presentation. This webcast will be archived for 3 months, so you can access it after today's live presentation. Within about a day, just simply use the same URL to access the archived webcast. Okay, with that, I think we're ready to begin. Our speaker today is Scott Margolin, the International Technical Director at Westex by Milliken. A former firefighter, Scott has spent years in the flame-resistant fiber business researching flash fires and arc flashes. Scott?
Thank you very much, Kyle, and good afternoon, or I guess good morning, everyone, as the case may be. Excuse me. Today's webcast, I want to make what I hope is not necessarily an apology, but a comment up front. There's a whole bunch of video, and it's going to come later on in the webcast, and because of the nature of the technology, we've combined the video. You'll have 2 sections of video that will run, one for about 1.5 minutes, 2 minutes, and one for about 5 minutes. I will do my best to narrate at a reasonable speed while they're running. If they don't run at the same either at all for you or at the ideal speed, we will provide everyone with a hyperlink to the exact videos in the exact order that will be in today's presentation, so you'll have access to them. Okay, so with that out of the way, I think it's always important to understand who's speaking to you before we get into it. Westex by Milliken, you may already know, makes flame-resistant protective apparel fabrics. We do not make the garments. And the vast majority of the folks on the call today are not going to purchase fabric. They're going to purchase garments. So I don't have anything to sell you, but that raises the question, what is a fabric guy doing here? Why are you listening to me today? And the answer is really quite simple. The answer is that what gets the rating, the protective rating, the 2112 NFPA standard compliance, is the fabric brand and weight. It is not whether it's a red coverall or a blue shirt or whatever. It's what the fabric brand is, what the fabric type is, what the fabric weight is. That's what determines the protection afforded in a combustible dust flash fire. It's also the fabric brand that determines the durability of that flame resistance to laundering in the environment. It's the single biggest cost component of a finished garment in most cases. It's a huge piece of how comfortable the garment's going to be, how long the garment's going to last. So most of the technology is in the fabric, and as a consequence, it's what people specify first, and that's why it's folks like me who get to blow the stuff up and tell you all about it. So what we'll do here, we'll go over combustible dust for a little while, and then the second half of it will be how do we protect workers against this flash fire hazard. Why is combustible dust getting the attention it is? You probably have already seen these numbers. If you haven't, there are an awful lot of incidents, and unfortunately, when they occur, they are catastrophic or fatal a large percentage of the time. The most famous one in the U.S. was Imperial Sugar. That's what caused Congress to demand OSHA create a rule. Imperial Sugar killed 14 people and hurt over 40, and the vast majority of those fatalities and catastrophic injuries were a result of burns, and most of those burns were a result of clothing ignition. That part of this is avoidable. And so after that, you may know, OSHA created a national emphasis program and has been actively citing people in certain industries. And I don't want to bore us with all the details, but if you need the data to support what's going on here, here's a little bit more of it. You can see the red is injured, and the peach color there is how many folks are killed by year. And what you notice about that, one obvious thing is the trend line. The trend line is quite steadily up and up a lot, and there are a variety of reasons for that. The events, in this case, engineering can reduce the frequency and the severity of these events, but it can't eliminate them. But the engineering combined with personal protective equipment and some behavioral safety can really help fix this. And what blows up? What industries are we really talking about here? You can see a nice layout here. some of them are probably obvious to you, like food and wood. Some of them may be much less obvious to folks who are not familiar with combustible dust. Things like metal and plastic surprise a lot of people. You might be familiar with what happened in China about a month ago. There was a wheel hub plant in China that made parts for a major American automotive manufacturer, and the fatality there, the last number I saw that I found credible, was north of 170 people dead, and just a huge number injured, hundreds injured. And that was a combustible dust event in metal, and that's something that surprises a lot of people. What industries are vulnerable? Well, it follows from the previous pie chart, doesn't it? And so if you find yourself on one of these pie charts, these are the folks that the OSHA National Emphasis Program is targeting as industries that have either a history of combustible dust accidents industry-wide, not specific to a company necessarily, but to the hazardous substance, and or a KSP value that they find problematic. And we'll get a little bit more into that. So when you have a combustible dust issue, what do you have? Well, it's a flash fire. And if a flash fire occurs indoors, then you can also have damaging overpressure. If it occurs outdoors, you typically do not. But what a flash fire is a diffuse fuel in air. So we're not talking about a pile of something on fire. We're talking about that fuel becoming diffuse in air the way that a dust would if, for whatever reason, it was on your drop ceiling or on your floor or on the top of venting and it was knocked into the air. But if it hits the right concentrations with air, it's flammable. So you add that diffuse fuel in air with a ignition source of some sort. Sometimes it's an arc flash, sometimes it's something else, and it'll ignite. The good news is, once it ignites, because the fuel is limited, it's diffuse and it's in air, and because it ignites at one point, the flame front will move rapidly through that fuel so that it's not on fire for very long in any single location because the fuel is diffuse, and therefore the fuel is used up very, very quickly. Because it's not on fire for very long in any single location, we can save people who happen to be standing in that location without having necessarily to need turnout gear and SCBAs and all the rest of the protection that you can't get anybody to wear for an 8-hour shift. Because it's a second or two, maybe 3 seconds tops. It is a survivable event in the right PPE, and that's PPE that you can wear all day, every day, so it is viable. And the problem with it is, as this happens, as the flame front moves through the cloud, it can also, if it's indoors, create a pressure wave ahead of it that lifts more dust ahead of it so that it self-perpetuates. But it self-perpetuates through a facility. In other words, where one might be standing, the event is going to be very, very brief, even if it takes 6 or 8 or 10 or 12 seconds for the thing to put itself out from start to finish. But it won't be on fire for that long in any single location. It'll be moving over a large distance for that period of time. I'm not the greatest artist, and these are not my drawings, but I probably couldn't do any better, so we'll use these. But what you can see, you have the initial deflagration. You've got a shock wave or a pressure wave caused by that lifts dust in the air in adjacent areas, and then that allows the fire front, the flame front, to move through that cloud. And it'll, again, move through that cloud very, very rapidly, consuming all the fuel as it does so that the event in any single location should not last more than a couple of seconds. And again, that becomes critical in a bit when we talk about how to protect against this hazard. So those are the real quick facts on it. What's the regulatory background look like? Well, the House of Representatives passed a bill after Imperial Sugar, but not a lot has happened since then, unfortunately, or fortunately, depending on your point of view. It did stall in the Senate. OSHA created a national emphasis program as a result, and the purpose of that program, as you can see, is, again, to inspect facilities where this stuff happens frequently and kind of get ahead of a rule and increase enforcement, increase awareness, even if the rule didn't happen or while the rule was being debated. There are a number of standards, and unlike some of the other issues you might be familiar with for arc flash or other flash fire, there are a bunch of both OSHA standards and NFPA standards that bear on combustible dust. So one of the challenges has been correlating either the legal or practical or technical aspects of these standards, and I won't go through them in detail. You have access to them here. It's kind of a reference list to know what's being said about combustible dust by OSHA and by NFPA. Now, the NFPA list you have in front of you now, there's one in red on purpose. Typically in the past, the NFPA standards that bear on this subject were specific to a single industry. So let's say wood or grain, as you can see. 654 is in red because it came along and it tried to be a generalist standard. And I think that's a good thing when you've got a dog's breakfast of arguably competing and certainly different in terms of what they say and what they don't say is acceptable. standards. And what does OSHA do? OSHA tells us what we shall do, but not how to do it, right? So when OSHA creates a rule or decides to enforce something, they typically lean on an industry consensus standard to do so. So they'll say you shall protect your employees from a combustible dust fire hazard, but they won't tell you how to do it, and then you go to typically an NFPA consensus standard to do that. But what do you do if you've got a dozen of them? How do you pick which one? And so 654 at the moment would appear to be, and I don't have a crystal ball, and I'm not an all-seeing czar of this issue, but 654 at the moment would appear to be the catch-all standard, the generalist standard. And so we'll take a quick look at what that is, and also the possibility of another standard called 652 that's coming down the pipe. 652 is mentioned here. 652 is attempting to, if and when it's completed, it's not yet, it's a new standard, and there's a technical correlating committee working as well. But it's attempting to become the generalist standard for all of these as well, and it may supplant 654 when that happens. In the meantime, what does 654 say specific to flash fire and protecting workers? Well, in 11.2.3, it's pretty clear. It really doesn't get a lot clearer. It recognizes that you can engineer the hazard down in severity and frequency, but not out, and therefore we still have to protect people. And what it says is that maintenance procedures shall address, that's proscriptive language, it says shall address personal protective equipment for tasks involving, it goes on and on. It says PPE shall include flame-resistant garments in accordance with workplace hazard assessment required by 2113, and where a dust explosion or flash fire hazard exists, flame-resistant garments shall be required for all exposed personnel. So that's really clear the way these things go. It says you have to do it. You have to include the flame-resistant clothing, and it points to the 21, 12, and 13 standards for flash fire as a way to evaluate your hazard and the clothing. That's pretty clear. What is going on right now? Well, OSHA can and is citing facilities at the moment, and you could certainly make the argument that there's more in place, and from an OSHA perspective, to enforce combustible dust than there is for NFPA 70E, if you're familiar with that. And 70E on the electrical arc flash side is a huge standard in the country, and most people are complying to it. What's going on with dust at the moment is there are industry consensus standards which have proscriptive language around FR clothing, like for NFPA 70E, and OSHA in this case has something additional, which is the National Emphasis Program and the Path Toward Rulemaking. So you certainly could argue that there's more OSHA activity around dust than there is around 70E, and yet compliance lags. One of the things that's different is that you could be held civilly liable in this case, at least at the moment, and that's causing states to act as well. So the focus industries we looked at before in pie chart form, if you're more comfortable seeing them written out than having to read the tiny print in a pie chart, I put this one together for your reference as well. Some of that, again, is obvious. Some of it's somewhat less so. But it's important to take a look at what has blown up, not just what's happening out there, and we'll do that in a moment. When you look at the OSHA instructions in the National Emphasis Program, we saw a moment ago what NFPA had to say about it, but we didn't see what OSHA has to say. So it's quite specific here as well. It's called out for you in the part, but the red is obviously what I chose to highlight. It says one feasible abatement method to correct the hazard, and the hazard being combustible dust flash fire, is to require employees to wear flame-resistant, non-static generating clothing. So again, that's very, very specific. And while I don't have an absolute knowledge in this area, and I'll tell you that right up front, people who do know have repeatedly told me that all four versions of the rule that OSHA submitted to SubREFA some time ago have the same proscriptive language around FR clothing. Not necessarily word for word what you see here, but that it is required in all four versions. One of the things that they fight against now typically is housekeeping violations, and as a subset, you see the other things in there. One of them, I believe it's the fifth most cited when NEP comes out and taps on your door, is personal protective equipment, and typically that's FR clothing. And you can see an example here of a specific violation. Again, I don't expect you to read this right now, and in the interest of time, we don't need to go over it, but suffice it to say, if you want evidence that it's happening and happening now and the costs to people, here's an example for you to take a look at your leisure in more detail. Obviously, you can go to the OSHA site and get more of these. So pulling the fines out from the detail level to the higher level, you can see what some of the big ones have been recently, and they're pretty hefty fines. And in fact, the Imperial Sugar fine, when it was first levied, was the largest fine in the history of OSHA to date. Now, as you probably know, many of these get reduced over time as the legal wrangling goes on, but they get reduced usually commensurate with the initial number. I will tell you that the OSHA fine is probably the smallest check you will write if you have one of these incidents. In many cases, these incidents destroy the facility, which has obvious implications. And on the human side, burn injury is the second most expensive hospitalization medical care that I'm aware of. It's extremely expensive, and typical body burn that requires a burn center, you're talking about 30 to 60-day stays. It's probably $100,000 for the first day or two while they run every test in the book, and then depending on where you are, $10,000 to $20,000 a day beyond that. Plus, you have to have a reserve fund that meets or exceeds your initial monies paid. And so a single burn injury where you have significant injury because of clothing ignition, you're talking about millions and millions of dollars per person. And these are costs that often will go on for the rest of that person's life. So, again, while these numbers scare people, they are probably the smallest check you'll write if you have an incident, unfortunately. So how do you analyze whether a dust that you have is combustible, and if so, how combustible? Well, you've got something called KST, and this gets pretty technical, and I don't want to bore you with the details, but KST measures both whether something's flammable and if it ignites, what kind of problem it's going to cause you, and it's mostly pressure and expansion based, not necessarily, we're not necessarily talking about flame temperature or anything like that, but it's a fairly simple test to do, and you get a categorization where its KST is 0, 1, 2, 3, or 4. And you see that KST 0, there's no risk of explosion. You do not have a combustible dust. If your report comes back KST 0, you don't have an issue. At least that's one interpretation of the rule. However, the part where you got to be careful is if you have a KST of 1, your KST value is 1, well, that's weak. It says weak explosion if you look at the light blue letters. Well, that doesn't sound like a big deal, right? I probably don't need to worry about FR clothing. It's weak. Well, folks, the vast majority, and some would argue all, but I'll say the vast majority of the multiple fatality events we've had with combustible dust in the United States in the last couple of decades have all, or most or all, been quote-unquote weak KST value, low KST value dusts. If there's any KST at all, anything over 0, a KST of 1, that's flammable. Now, it's not necessarily very explosive. You don't necessarily generate a huge pressure wave, but it is flammable at a KST of 1. And if it's flammable, you do have the flash fire hazard, so you do have the obligation to protect the employees from that hazard. Take a little closer look at it. I'm calling these out by specific event. We're leaving the company out, but you can see, if you know anything about combustible dust, you can figure out who's who here. You can see what blew up, phenolic resin, coal dust, scrap tires, how many it killed, how many it hurt, and the reason for the explosion. It happens in a wide variety of industries, for a wide variety of reasons, unfortunately. And then you look at this next chart here, and you can see some extraordinarily high numbers of injured folks. What do all of these 6 have in common? I'll give you a second there to look down those. What do they have in common? Well, you can see the KST values, all of them below 200. Therefore, all of them classified as low KST, and yet if you add up the numbers of killed and wounded in those events, you don't even want to think about it. It really is something you need to be careful with. I wish that the folks who decided what we would call these categories in KST come up with better words than weak and low, but it is what it is. You need to be aware of it. Anything with a KST of 1 or higher is a flash fire hazard, which requires flash fire protection. So, what do we do about all this? Well, you've got National Safety Council recommendations, and it's quite clear. It's written for you here, and again, the red stuff is highlighted, or I should say it's pulled out of the document. The red stuff is highlighted. But what it says is, even if controls are put in place, potential for dust explosion still exists. Because, again, we can engineer these things down but not out. We can't guarantee anybody anything. And so, once that's the case, protection of all employees in affected areas is accomplished through the use of PPE such as FR clothing and ongoing training. That's pretty self-explanatory, pretty simple, and very consistent with what both the NFPA standards we looked at earlier and the OSHA NEP say on the subject. So everyone's kind of in agreement here. So how do we mitigate this hazard? Well, the obvious one is to control the dust, right? We start with whatever we can do with air handling and housekeeping to reduce the presence of combustible dust in large uncontrolled areas where it could ignite. And then, secondarily, we look to control possible ignition sources in the area. Unfortunately, arc flash causes a bunch of these, and as long as you have energized electrical equipment, well, you don't plan on it arcing, obviously, but if it does, you can have a problem. So there's usually an ignition source no matter how much control you do. All right, well, after that, we control the presence of the fuel We control what we can control for ignition. Then we're looking at damage control if something should happen. And the damage control there is things like blast vents to let the pressure wave out of the building rather than bringing the building down on top of people. And obviously, protecting those people from the thermal event that might occur. And as I mentioned, both OSHA, Chemical Safety Board, NFPA, and NSC all call for PPE, flash fire PPE as part of this now. So when we come back to 654, take a little closer look at it. As I mentioned earlier, it says workers shall be protected. Well, when? How do we know? As part of our hazard analysis, all right, what more do I need to know about that? Well, basically, a 64th of an inch of dust is all that it takes. That means if you can't see the paint color through the dust, you've got a problem. Some other people will say it's the depth of a penny, but everybody's got their own take on it. The bottom line is that it doesn't take very much dust at all, either in depth or in what surface area of your plant it covers, to get trouble. I mentioned 652 was looking like it might supplant 654 as the catch-all standard. What does it say about this? Well, it also has the same proscriptive language around flash fire and protective clothing to flash fire, including the words shall include and shall be required. And again, if you're not familiar with the standards and the regs, when you see the word shall, it's removed choice. It's not an option. The only thing you can really do at that point when you're told you shall be required is through your hazard analysis to determine who shall be required and who doesn't need it necessarily. But if the hazard's there, then the issue's there. So how much? I mentioned a moment ago, it doesn't take much. If a facility is smaller than 20,000 square feet, all you need is 5% of the surface area to have dust on it. And, folks, that includes every horizontal surface in the building, meaning floors, drop ceilings, venting, ductwork, machinery, anything that could catch dust. You might have tarps hung above operations. All of that adds up. And if it adds up to over 5%, 64th of an inch deep, you've got a problem. With a larger facility, you need 1,000 square feet. That sounds like a lot, but when you think about it, you do the math, that's a circle of an 18-foot radius. That's it, or a 32 square foot square. That's it in a facility of any size once you get above the 20,000 square feet. So it doesn't take much surface area-wise. It doesn't take much depth-wise to trigger a problem. So when you come back to what we do to the personal side of it, right around halfway done, hopefully, let's start to focus on the flash fire hazard. Again, we talked earlier, it's a diffuse fuel and air with a rapidly moving flame front, which means it lasts a very short period of time in any single location, which means if the people in that location are wearing clothing that doesn't ignite, we can save them. And we'll take a look at why that is. See, the videos are coming up. I'm hoping that they'll work. But let's turn the page now that we understand how we get to a flash fire and explore a little bit more what a flash fire is and what we can do to protect against it and how you would evaluate the options to protect against it. The definition in a couple of places, including 2112, which is directly referenced by these standards, notice it's an unplanned exposure. We're not fighting a structural fire here. We're not putting on firefighters' bunker gear. We're supposed to be able to wear secondary protective apparel for accidental exposures to a hazard like this. And it talks about a moving flame front. And it says there in red, typically 3 seconds or less. Why is it in red? Those words were removed very, very recently because it was felt by some folks that we wanted to expand this category to include fuel-fed fires and give you escape time to run away. But the fact is that you can't unring a bell, and for 20 years the standard said 3 seconds or less. And it said 3 seconds or less for the duration of one of these because that was the physical limitation of a flash fire because the fuel is diffuse and the flame front moves rapidly. Why is that important? Why am I emphasizing that? Because when you turn the page from research to actually acquiring what you need to acquire, including FR PPE gear, you're going to see marketing that's all over the place. You're going to see competing sales claims that are all over the place. So it's critically important to understand what the standards say and what the science says, and for that matter, what logic says about what the hazard is and isn't. And it's 3 seconds or less according to these standards for a very long time. So what's the difference between a fuel-fed fire and a flash fire? Well, again, the diffuse fuel is a limiting factor, isn't it? In a fuel-fed fire, and of course, a combustible dust flash can cause a fuel-fed fire that then goes on for an indeterminate period of time until, you extinguish it or days later. All we can do in secondary protective apparel, single layer PPE like this, with no SCBAs, no breathing apparatus, no face protection, no airway protection, all you can do from a fuel-fed fire standpoint is run away. You're just trying to buy time to get away from that thermal event. In a flash fire, though, the protective apparel can do everything that you need it to do ideally. So what are the standards that are relevant to looking at flash fires? And I apologize that there are so many standards coming at you right now, but one refers to the next, and it's all relevant. NFPA 2112 and 13 are flash fire standards. The ASTM 1930 standard is a test methodology. It tells us how to do mannequin testing to determine the protective performance of various FR fabrics, but it doesn't tell us what passes or what fails. 2112 comes along and it says, hey, 1930 is a pretty cool test. That makes a lot of sense. Let's create a pass-fail standard here based on that test methodology. So 1930, again, is how to test the fabrics to a flash fire, and 2112 tells us what to test for in that flash fire. There's a lot of other stuff behind 2112 as well that's more detail-oriented, but most people, when they refer to 2112, are primarily referring to the mannequin test, which shows you a body burn percentage, second and third degree combined. 2113 is more about hazard analysis and how to select garments and less about a test requirement. So hopefully that makes sense. There are 3 labs in North America that can do this testing. 2 of them are independent university labs, one at North Carolina State in Raleigh and one at University of Alberta in Edmonton. The third is in Richmond, Virginia, owned by DuPont Nomex. And while it's a 1930 certified lab, obviously it's owned by a commercial interest, so people go to either NC State or University of Alberta to do their research. So why is 2112 important to you beyond the fact that it's pointed to by all or most of the relevant combustible dust standards? Well, number one, it defines a flash fire for us. Number two, it sets the pass-fail threshold I meant. It says that a flash fire is 3 seconds max. So you test the garments at 3 seconds. Why are we testing the fabrics at 3 seconds? Well, number one, it's the defined upper limit of a flash fire. And you want to test worst-case scenario, right? You don't want folks reporting what might happen in a 5-mile-an-hour car accident when you have a risk of a 30-mile-an-hour car accident. That's why stuff is tested at sort of extreme conditions. And the other issue with testing is when you test something and you're specifically looking to report differences between items. The whole point of this testing is to show performance differences if they exist between items. Well, if you test everything at 1 second, it all looks great. And if you test everything to 5 or 6 seconds of fire, it all looks terrible. So what would be the point? So 3 seconds also happens to be the duration of maximum difference between the various fabric options. And so on both levels, it's the appropriate time to test. So the good news is you've got a pass-fail standard. You can say to yourself, oh, I've got to comply to 2112, so anything that complies to 2112 is okay with me, and you would be legally sound. Now, I have serious reservations about the ethics or the morals of that. Maybe those are inappropriate words, and I apologize if they're overly judgmental. But what I mean by that is there are vast differences. There are huge differences in performance between compliant products. It is very important to understand what the standards say and what they don't say. And when you take a closer look at what the standard's telling us, you might be a little bit concerned, and you'll see where I'm coming from. So the 1930 testing, again, you take a standard-sized garment, a standard mannequin, and you surround it with fire for a controlled duration. You take data for 60 seconds to make sure you capture everything that you can capture, and you go from there. So let's take a look at how we know these things last this long. I'm hoping that the video coming up here will play for you. But let's see. So in the real world, how do we know what's going on? Well, what we did to answer this question, are these flash fires 2 seconds, are they 3, are they 4, are they 5? To try and put the sales and marketing spin to bed, let's say, all right, let's take the same sensors that we use in the laboratory and make them portable. And let's find a facility outdoors where we can create real flash fires, full-scale outdoor flash fires, where we can release a diffuse fuel in air, ignite it, and see what happens. With the sensors in the way, and the sensors would then tell us exactly how long the fire lasted in that location and exactly how hot it got. So that's what we did at a facility called Peaks, which is part of Texas A&M University in College Station, Texas. Again, I hope this video plays, and I hope it takes the minute and 50 seconds it's supposed to take. I guess we'll find out together. If it doesn't, you can catch it on our website. So what we have here, hopefully you're seeing this, is you're seeing you're seeing a flash fire at the lab. One of these garments is flame resistant. One of these garments is not. You passed my class today. If you can tell me which is which. Now, who would you rather be? why do you need flame-resistant clothing in a flash fire? Well, really, we spent 30 minutes talking about some of this stuff. This is really all you need to see, right? For the guy on the right, the exposure was over at 3 seconds. So you're not worried about breathing fire and doing damage to your airway or your lungs or your face. For the guy on the left, it went on and on and on. How long does it last in real life? Well, what you see there, the black dot, is one thermocouple that measures heat, like what's on the mannequin you just saw. You connect one thermocouple to one data logger, which is basically a hard drive. You put a whole bunch of them in harm's way. What you see now, all the silver ones are these data collectors, these thermocouples, and we're putting them at the center of human mass. That's why they're all set at that height. That's where your workers are, right? And we're facing them out from the fuel source, no matter what the wind is doing, no matter what the wind speed or direction are. Some of these sensors will be in position to catch every flash that happens. Now, we repeatedly release the fuel and ignite it and measure. Release the fuel, ignite it, and measure. The white stuff there, that's insulation to protect the hard drive, obviously. You don't want that thing melting. And if you do enough of these, if you put enough of these sensors in harm's way and do enough flash fires over enough days in enough conditions, you get a ton of data. This is what it looks like. You see the fuel, and then it hits the fire that's at the left margin, and it flashes back. 2 seconds total, 2.06 seconds total to traverse 60 feet. Okay, 2 seconds to go 60 feet. By the time it gets to the right side of your screen, is it still on fire at the left side of your screen? No, it is not. Why not? Because it's a diffuse fuel and you've used all of it up. So while it took 2 seconds total to cover that distance, how long did it last where any single worker was standing? Less than that. Okay, well, the video is cool, but what we really tell the story here is with data. And hopefully you saw that well, and it's over for you now. And we'll put the next slide up. This is boring, but it's a picture of the fire field you just saw. In the center is the fuel release. The 2 circles around it are where the sensors were positioned. And I'm just showing you a little bit behind the scenes how this research was done. By the way, this is University of Alberta and Texas A&M TEEX, not West Tex, conducting this research. It was our idea, and we paid for the TEEX facility and the propane, but the research was, what's the right word here? The design of the research and the conducting of it were by University of Alberta. And so there's a photograph of the fire field in real life. What do you see here? This is pretty cool. You see 2 mannequins standing in a fuel cloud. You see a fireball approaching them, but it's not got to them yet. Is the flame front moving? Clearly it is. Clearly it's not on fire at the mannequins yet, right? So it's not all on fire at once. Another similar view. This time the stuff drifted away from our mannequin. It ignited at the back of your photograph. You see a gap between that fire that's permanently lit at the back left and where the fire is right now. So you see where the flame front is, you see where it was but isn't anymore, and you see where it's about to be in the form of the white fuel that's not on fire yet. These things clearly are rapidly moving flame fronts. Why is that important? Again, because it means it's not going to last very long where your worker's standing. So how do we know how long they really last? This is the most boring slide I have, and I apologize, but I don't want to stand here and say to y'all, hey, these things are 3 seconds or less, for sure, real-world proof, without showing you the proof. So what you've got in front of you, forget the middle graph for a minute. Look at the 6 graphs that are sort of a clock face around it. Take any one of those that you want. The horizontal axis is time, and the vertical axis is heat flux, or if you want to look at it another way, temperature. So what you have is that as it goes along flat is no fire, no fire, no fire, and then suddenly you see a peak, an upside-down V, a mountain, whatever you want to call it. That's the fire. The width of the opening, if you make your a peace sign and turn it upside down, the opening between your fingers, the opening at the bottom of any of these blue upside-down Vs, that's an exact measure to the 10th of a second of how long the fire lasted at that location. So if you have 36 sensors in position and you do 80-some flashes a day times 3 or 4 days a week times several visits to the facility, you end up with an enormous amount of data, and guess what? Not a single flash fire in a single location ever lasted 3 seconds, much less more. They average much less than that, typically around 1.75 to 2.2 seconds, period. So now we know what the hazard is. And for the last third of the webcast, let's turn our attention to how we protect against this particular flash fire hazard now that we've got it designed, figured in our mind. Flame-resistant fabric. What's a burn? What are we looking to protect against? What can the fabric do for us? This is kind of an important slide. It's a little bit off topic, but I think it really underpins everything else we're discussing. Let's discuss the medicine and what kills people in a burn. What we measure when there's a burn victim, and the friends, the family, the coworkers are gathered in that waiting room outside the ER, and they're waiting for the surgeon to come through those double doors. And the first question everybody asks every time is, will he live, or will she live? Will they make it? What's in the burn surgeon's mind in that moment to answer that question? The answer is basically two things. There may be some others, but by far the two biggest predictors are the age of the victim. The older you are, the less likely you are to survive, and the TBSA, or total body surface area, that receives second or third degree burn. So if you know burns, second is blisters. It hurts, but it heals, and it typically doesn't scar. And if it's a small enough area of your body, it doesn't even require medical intervention. Third degree is full thickness, skin death, won't grow back. Now you need grafting, agonizing, disfiguring, painful, frequently surgeries forever. So third degree is clearly way worse, right? So wait a minute. If third degree is that much worse, how can they possibly be the same for predicting fatality? You know, Margolin must be off his rocker to say that. Well, what does second and third degree burn have in common that makes them the same for predicting fatality? The answer to that question is what drives the existence of the entire FR business on the planet, and every standard written about it, and every test method that determines how protective something is. So that's why I thought it was so important to share it with everybody. Second and third degree burn both have in common they break the skin. It's that simple. They both break the skin. And once you break the skin, you have an infection path, right? Where do they take you when you get hurt? A hospital, don't they? Or a burn center. Where there are more infectious agents than anywhere on the planet, including all the antibiotic-resistant ones. And that's it in a nutshell, folks. The greater percentage of your skin surface is broken open, and second and third degree both do that, the more pathway you have for infection, I mean it's more likely, and the longer you're in the hospital around the bugs. So, if that's what's killing people, death from infection from high percentage body burn, not 2 or 3%, not 10 or 13, the percentage body burn above which it's suddenly much more likely to be fatal is 50%. We saw a moment ago that these flash fires, these dust flashes, are directional events. So if you're working naked, and I'm not advocating that, but if you are, and you're facing an oncoming flash fire, what's your maximum body burn? Maximum, if you're naked. It's half, right? Maybe less, minus the soles of your feet. Well, if over 50% body burn is what's typically required to cause infection and fatality, and you're burned over less than 50% of your body if you're naked, what is almost required by that logic to cause fatal levels of body burn in a directional event like a combustible dust flash or an arc flash? And the answer is clothing ignition. Don't wear fuel. Don't work in an environment that has this risk. If you have the risk, recognize it and dress to it. Don't wear fuel. If your clothing doesn't ignite, your body burn is going to be limited to the area that the thermal event hits you, which is less than half or half your body. If your clothing does ignite, now your entire body is at risk. It's that simple. And it's that easy. I shouldn't say easy, but it's that basic to fix it. Don't wear flammable clothing if you have the hazard. So how do you take a look at what's out there available to you? Well, you might have heard the marketing terms like natural and synthetic, as if natural is always good and synthetic's always bad, or the flip side of those terms, treated and inherent, because all synthetics are treated. all the inherents are synthetic and all the treateds are natural. It's all BS, folks. It's marketing terms with no basis, really, at least the treated and inherent portions of it, in textile sciences. What should matter to you guys when you specify fabrics and purchase them and wear them is not how the engineering was accomplished. What should matter to folks is that the engineering was accomplished, right? So that 6 days later, 6 weeks later, 6 months later, heck, 6 years later, the stuff that you get out of your drawer or out of your locker and wear to work is FR, no matter how many launderings it's been through, right? That's what matters. You shouldn't have to count launderings. It shouldn't be based on some de minimis standard. And by the way, the standards are by definition de minimis. They're all minimum standards intended to include, not exclude things, and almost everything can pass almost all of these standards. So what do you do about that? Well, I would urge you to look for proven products. I mean market-proven products, because people vote with their pocketbooks ultimately. I'm not a big fan in the safety business of trying something new that looks cool in a trade show booth or trying something that 3 or 4 people bought 2 years ago. I'm a big fan of they bought it. When it wore out, they bought it again. When it wore out, they bought it again. And over 2 or 3 buying cycles. And then granted, that's 6, 8, 9 years for most products. If enough people in enough companies over enough industries buy the same thing, well, I start to go, that must work. It must work pretty well. And the 80-20 rule is in full effect here, folks. More than 80% of the business for flash fire protection, dust and other, in the United States today, more than 80% of it is enjoyed by less than 20% of the fabric offerings out there. There's that big a disparity. So we're going to take a look at another video for you now. All 5 of the products you're about to see, and this is a 5-minute clip, I apologize. Normally, what you'd have here is 5 separate clips, and we can talk about them. But in this environment, we're going to show them all at once, and I'll try and talk to them as they're happening. But they all comply. So if you simply say, hey, man, I'm busy, and 2112 is all I really have to do is comply with that, so I'll take anything that complies with 2112, because they must all be equally good if they all comply, and then I'll buy from whoever's the cheapest, or whoever took me to the nicest golf game, or whoever took me out to the nicest dinner, whatever. That's an understandable attitude when people are busy. But let me show you, part the curtain here, and show you why that's dangerous in my opinion. So what we have here is the official lab testing. This happens to be the University of Alberta. Fabric B, and you'll see a 3-second fire fully engulf the mannequin from the torches. And what we're looking for is it still on fire when the fire goes out? Well, no, this one wasn't. Did it shrink up or did it shrink in, which would both reduce the insulation and potentially expose skin and flammable underlayers? Did it melt? Does it have holes in it? Does it look horribly damaged in some way, shape, or form? If it shrunk, did it shrink so badly we can't get the zipper down and the coverall off? Because what's the first thing you want to do? Well, get the coverall off, right? So release heat and get yourself cooled off. And then we look at it again in slow motion. And if there's any after flame, we can see the after flame. And when I say slow after flame, I mean when the torches go out, is there any fire on the garment? If there is, how long does it last, and what percentage of the body surface area is it covering? Now, this time we didn't have any. So the visuals are cool, but don't be misled by the visuals. They're nice, but what matters is the data, and here's the data. 8% body burn, all of it head and neck, none of it through that FR coverall. Your head and neck would not really be burned like that in real life because you have a hard hat, safety glasses, nobody stands still for 3 seconds, they don't last that long. All right, another fabric that also complies to 2112. This time you see a little after flame on his left elbow. You see a little bit more smoke. This is a little bit lighter weight of garment, so it's not going to do quite as well. It still complies. You still don't see any shrinkage up or in. You still don't see any visible garment damage, which is not necessarily bad, but you want to see it if it happens. When we look at the T-shirt, why are we showing you the T-shirt? Because if the T-shirt's undamaged, that's suggestive. This one's a little bit damaged. Not a lot, a little bit. So we know some heat made it through our FR coverall, even though it didn't burn. In slow motion, we get a good look at the after flame. We see that it's on the left elbow. It's very limited in surface area, which is critically important, and very limited in time. And it goes out right away. That's called self-extinguishing. That's what we want to see. Again, it's the data that really tells the story here, folks, though. Don't be misled by the visuals. The data on this one is percent and change. And now we have about 5% of that. The head and neck is about 7 or 8. There's about 5% of that is through the coverall on the sleeves. Let's look at another very, very popular fabric in the market. By the way, the last two and this one are probably 80% of the U.S. market. You see significant afterflame on this one. It's body-wide, and it lasts a couple of seconds. Obviously, that contributes to the thermal load. You see some shrinkage both up the cuffs and up the sleeves and in. In is arguably more dangerous than up because it has implications for getting the garment off and exposing skin, bare skin and or flammable underlayers. When you see the T-shirt this time, you'll see substantially more damage to it, and you'll see a pattern beginning to emerge on that T-shirt. That also ought to be suggestive to you that the FR, while it didn't burn, that's its first job. It didn't insulate terribly well. That's its second job. In slow motion, you get another look at the afterflame. And again, what do we want FR to do? We want it to not ignite and continue to burn. That's what saves our lives. This saved your life. But ideally, you also want it to insulate you to the hazard you have so you're not burned at all or you're burned over an absolutely minimal portion of your body. Kind of like you wouldn't wear a windbreaker into a blizzard, right? The jacket that's good at 5 degrees is not 55 degrees is not good at 5 degrees. Body burn here is 34%. You see most of the area outside the underwear. This test requires a T-shirt and briefs. Fabric C, again, still complies to the standard. The standard is 50% body burn or less. Still complies. This time, we have much less afterflame, but ridiculous shrinkage, enormous shrinkage. This is really shrink-wrapped to the mannequin, as you can see. This is not removable by the zipper. It has to be razor knifed or scissored off the mannequin. So while it did an excellent job of not continuing to burn and save your life, it's also 800 or 900 degrees Fahrenheit shrink-wrapped against your body, and good luck getting it off. And now you can see a very clear pattern on the T-shirt. That's single layer versus 2 layer. Where it's not burned, the pockets and placket. It's 2 layers of that fabric. 1 layer, it didn't burn, but 1 layer of it didn't insulate you adequately, did it? And that's kind of the lesson there. So again, you see less afterflame, but you're trading afterflame for shrinkage. And what matters, again, is the data. So let's take a look at the data. And we see this time that we're at 40% body burn. And now you see some of that body burn through not only the FRC, but also through the undershirt, which should be instructive. So those are the four most popular products in the country, and they all comply. This is one that's a relative newcomer. The fibers that it's made of are not, but in this blend ratio they are. You see something very different. This is a gas phase product rather than a solid phase product. So it chars instead of burning like the others, but it uses gas phase to accomplish that. So you have massive carbonization and an enormous amount of smoke to achieve what is supposed to be a similar result. So once again, what's critical here is not necessarily the visuals. They're helpful, but you can see from the T-shirt what you might be expecting when you get to the data, because now it's heavily carbonized. There's also 40-some%. Oh, I got ahead of it. I'm sorry. Forgot about the slow motion. So this time we're not looking at afterflame or shrinkage. We're looking at carbonization and smoke generation, and maybe wondering what those effects are on the person wearing the garment compared to what we just saw. But the mannequin catches what it catches, which is thermal issues, heat issues, body burn issues. And those, as you'll see popping up here in a moment, I already spoiled it, are a little over 40%. And this time, significant percentages through both the FRC and the T-shirt. So, folks, all of those comply with 2112. And so when I said earlier, and this is the body burn silhouettes for the 5 products we just looked at. When I said earlier, I implore you guys not to simply accept anything that complies, but to demand that data complies with what? This is why. You'll never see this otherwise. You can pass a test with a 100% A+, and you can pass a test with a 61% D-. If you have kids and they come home from taking an exam at school and you say, how'd you do? And they say, I passed. Is that okay with you? Or are you going to say, passed with what? I'm asking you guys, I'm begging you, understand what the standard says and what it doesn't say, what it means to you in real life and what it doesn't, and please demand the data. Passed with what? It gets even worse, folks. The 3 seconds is what we just looked at. That's highlighted in yellow on this graph. But as we saw, flash fires don't last that long. The vast majority of them are substantially less time. Some of the marketing out there would show you 4 seconds and only 4 seconds. What's the sense in that? If they want to show 4, as long as they're also showing 1, 2, and 3, I get that. But if they're all failed at 4, look at the body burn percentages at 4 seconds. Almost every product on that graph is at or over 50% body burn by then. You're either dead or catastrophically injured. That's not protection. That's survivability. We're looking to protect people. And by the way, if you're looking at 4 seconds, 5 seconds, at some point you're going to take a breath. If you're running away in one of these events, you're going to take a breath. And in a second or two in a fuel-limited, rapidly moving flash fire, you're unlikely to do much damage to your airway or your lungs. But in 4 seconds, come on. You're going to breathe or possibly breathe and do significant damage to your airway and lungs. But what about your face? The face is not protected by this PPE. What will happen to people's face and hands in a 4-second fire, a 5-second fire, as opposed to a second or two flash? It's at a bare minimum disingenuous, if not worse, to suggest that this PPE is appropriate in 4 and 5 second fuel-fed fire durations. But anyway, there's the data for the whole range of possible exposures for these 5 fabrics, and you can see the differences. There are clear and startling differences in the protective zone where it matters, in that 1.5 to 2.5, 3 second range where most flash fires are, and the duration of most flash fires are. We can protect people, but there is a huge difference among compliant products. So please look beyond mere compliance. The standards were correct, folks. Way back when CGSB and NFPA wrote these standards, they were right. Flash fires are 3 seconds or less. They knew what they were talking about. It's a fairly simple conclusion there. I don't know what's happened here, but I'm unable to, I'm clicking next and nothing is happening. I don't know what you guys are seeing. There we go. Okay. So we had a little bit of a stall there. So what do you conclude? If the standards are correct, and the flash fires are 3 seconds or less, that's one thing. What do you conclude about the standards themselves, though, when they tell you that the pass-fail is 50% body burn at 3 seconds? Well, that's a pretty minimum bar, isn't it? That's like passing a test with a 61. It passes, but I don't want a 61 D-. I want a 90-something A+, don't I? So since there's such a big difference among compliant garments, you got to conclude compliance alone doesn't adequately protect people, does it? Compliance is showing you survival, not protection. And by the way, it doesn't tell you anything about the durability of the FR, the shrinkage, the cost, the life of the garment and what it costs to own over time. So you really need to do your homework. Where the standard stops is where your homework starts, not where it stops. A lot of people are tempted to say, I've got a standard. All I've got to do is comply. I'm done thinking about that. I'll move on to fall protection. I'm begging you guys. Passing the standard, 2112 in this case, is where your homework should start. Don't even consider anything that doesn't pass it, because most things can pass it easy. But please do your homework beyond that mere passing and say passes with what? Passes with what? That's critically important. How the stuff is made matters. And in the interest of time, we're going to skip over the inherent and treated stuff here, except to say if that's what people are using to differentiate one of these fabrics from another, inherent and treated, you might want to chuckle, you might not, but you ought to know they're all treated. Every flame-resistant fiber and fabric you can go buy, all of them are treated by people, engineered by people using chemistry. None of it is magic. None of it happens absent chemistry. Both pass the FR are the same for treated and inherent. They both start out with naturally occurring flammable substances, typically oil in the case of the inherents and cotton or wool in the case of the treated. And in both cases, human beings, usually chemical engineers, get involved, and they use chemistry and engineering, folks, create fibers and then fabrics and then garments, and that's where you come in. And if those garments, if those fabrics are solid phase, life of the garment without an asterisk, flame resistant for the life of the garment, period, not an asterisk that refers to some de minimis standard or some set number of launderings, then you've got yourself something you might want to consider purchasing. Excuse me. So the bottom line with compliance, is it enough? One more warning for you. The FR durability in 2112 is 100 launderings. If you see the blue 100 under 2112 there. That's pretty good, 100 launderings. But what no one tells you about that is that that's a self-submitted sample. Are you going to submit a sample you don't know is going to pass? And by the way, no one ever checks it again. So what resemblance does that sample you submitted for testing 6 or 8 or 10 years ago, what resemblance does it have to what you're producing commercially a few months or a few years later with all the time and cost pressures? Sometimes it bears no resemblance whatsoever. And the laundering is done under perfect conditions, perfect chemistry and everything else, which don't exist typically in the real world. So we regularly see things fail in real life that pass the testing. This is one form of failure, a terrible one admittedly, but the fabric itself was toxic, and yet it was a compliant product. There's another form of failure in an arc flash. It was not a flash fire, it was an arc, but it wasn't supposed to burn, and it did. It passed the compliance test. It didn't pass in real-life laundering. Here's a third form of failure, which is called break open, another fabric that passed all the compliance tests but failed in real life. This, luckily, is the most common form of failure, and when I say luckily, it's because it's primarily a financial implication and not so much a safety one. But that's shrinkage. An awful lot of the stuff you can go get today that looks like a great deal, they say it passes the same test as that other stuff, as the fancy stuff, as the name brand stuff, but it's $5 less or $8 less or whatever. The vast majority of the time, the corners they've cut to get there are either the durability of the FR to laundering or the shrinkage control, and sometimes both. I'm not sure whether you're able to see the picture. I'm not seeing it in my audience view. There it is. Good. So hopefully you're seeing that. That's not a joke. That's 6 inches. So this is something that to save $5, $6, $8 on the cost of a garment, hey, instead of being 40, it's 32. That must be a good deal. But 3 months, 6 months later, you're throwing it out because it doesn't fit. Instead of the 3 years it should last. Well, that's no bargain at all. It's costing you money, not saving you money, right? So the bottom line with all that, how do you know what's comfortable? Folks, you can't judge comfort across a desk in an office. You simply can't. It isn't based on weight. It isn't based on numbers like air permeability or moisture regain or wickability. It's a whole bunch of things, and it's person to person. It's moment to moment. And because of that, the only way to judge comfort, folks, is a wear test. Put it on. Go do your job. And I don't mean for a week in April. I'm talking about a month in let's say, July or January when there's weather. Please don't be misled about the comfort properties of something across a desk. And by the way, because you're uncomfortable doesn't mean you're heat stressed. No single layer breathable garment is a primary cause of heat stress. Whether it's FR or it's not FR, whether it's long sleeve or whether it's short sleeve, whether it's heavy or whether it's light, what causes heat stress is not your clothing if it's single layer and breathable. What causes heat stress is poor hydration, lack of rest breaks, lack of shade, and illness or certain medicines that can make it worse. If the clothing is in that list of things that you got to watch out for at all, and on the NIOSH document, which is our main government document, it's dead last, what it says is, whenever possible, wear light-colored, not lightweight, folks, light-colored, loose-fitting clothing. And it also says avoid synthetics, wear cotton, and that's for the wickability, obviously. So that's the deal on heat stress. Laundering this stuff once you have it. The quality brands, you can launder all of them at home, industrially, or dry clean, but be sure that whatever it is you have the laundering instructions for that particular fabric. But the good stuff, again, you're not counting launderings anymore. No need for that. The prohibitions are liquid chlorine bleach and fabric softener for all of these. Layering is a good thing for arc and flash fire. If you need to layer up for whatever reason, 2 layers is generally more protective than the same weight at 1 layer. Last item here, and then we'll take questions. Once you've got it, like a seatbelt does you no good buckled behind you to turn the dinger off, this stuff does you no good in your locker or in your drawer, and it does you less good than it should if the sleeves are rolled up or the coverall is unzipped or you in some other way messed with it. So it's got to be appropriate to your hazard. It's got to be worn properly. It's got to be the outermost layer. And what you're wearing under it can't be meltable. Do you need FR underwear? No, you do not. However, whatever you choose to wear under your company-supplied FR clothing can't be meltable. It must be all natural, non-meltable fibers like cotton, silk, or wool, because the last thing you want is thermal energy that's coming through there and melting a meltable. And the last item, duct tape is not an approved repair fabric for this stuff. So that's my time. I appreciate yours. I hope the videos played for you. If they didn't, we will certainly get you a hyperlink to them. You see my info on the screen if you want to follow up with questions in private later, and I'll turn it back over for the open questions now.
Great. Thank you for that wonderful presentation, Scott. You covered a lot of bases. Before we get to the Q&A, and I understand we do have a few, I want to remind everyone of the evaluation survey I mentioned at the top of the hour. The survey should be appearing on your screen now, and we ask that you consider completing it to let us know your thoughts. Your input is important as it helps improve future webcasts, so please do take the time to fill out the survey. If you don't see the evaluation survey on your screen, please turn off your pop-up blocker. Okay, let's get to some questions. Scott, you mentioned OSHA in the beginning. Do we need FRC even if OSHA doesn't create a rule and even if someone doesn't add air handling and blast venting and et cetera?
Yeah, I see where that's going. It's saving money. The PPE is a lot less expensive than the other stuff. Yes, even if OSHA doesn't create a rule, they have the National Emphasis Program, and they are citing against it now. And there is, of course, the General Duty Clause, which obligates people to protect workers from recognized hazards. Flash fire is certainly a recognized hazard. Combustible dust, flash fire certainly are as well. So a rule would make OSHA potentially very aggressive, but absolutely there's still an obligation even today to protect exposed workers, and that includes FR PPE. Okay.
You had that body burn graph earlier, that the stuff we're looking at getting shows a body burn graph that goes from 3 to 5 seconds. You touched on this a little bit, but why do they do that if the standard is 3 seconds or less and the test is 3 seconds? So why is that allowed?
I gotcha. Westex always shows from inception of body burn through failure. So we're showing a graph from 0 seconds. Well, there's no such thing as 0 seconds. That's no fire, but from a fraction of a second on up to past 3. I think what the question might be after is some of the marketing for some products out there. They show a chart at 3 seconds and above, not 3 seconds and below. And if that's what the question is saying, everybody has entitled to their own opinion about why that's done. But to me, it's disingenuous, and it's avoiding what the standards say the hazard is and what science says the hazard is. If you want to show 4 and 5 seconds, you're welcome to, but not in the absence of showing 1 and 2 and 3, where the vast majority of these hazards exist. So to me, what that is oh gosh, I don't want to be that judgmental, but what leaps to mind is smoke and mirrors. What to me it is ducking a portion of a burn curve where your product doesn't do as well as your competitor, and so you choose not to show it. Obviously, okay. I don't know what's in anyone's mind, but that's...
Great. What if a person's tasks, a worker's task, their job involves things like grease and oil? I mean, that's likely to get onto the clothing. What kind of effect does that have then?
If there's a flammable contaminant on top of your FR, it runs the risk of igniting in a flash and burning. So the good news is, versus a flammable coverall or whatever, the fire won't spread to areas of the garment that are uncontaminated with that grease or oil because it's a flame-resistant garment. But that contaminant will burn on top of it. You'll still get burned through it. So the rule here is get them clean and keep them clean. If you can't get them clean, replace them.
Okay, fantastic. Unfortunately, we are running out of time. I apologize we didn't get to everyone's questions, but all of the questions that have been submitted but not answered will be forwarded on to Scott. Once again, I hope you take the time to fill out the evaluation survey on your screen to give us your feedback. And with that, that concludes Safety and Health Magazine's webcast. I'd like to thank Scott, West Tex by Milliken, and everyone who listened in. Thank you, and have a great day.